Right, question 11 is about thermistors and how they're used in a potential divider circuit. So this was fairly straightforward, or should have been fairly straightforward. But what we got here is a thermistor. We've got the voltmeter measuring the voltage, the current measuring the ammeter measuring the current, and a fixed resistor. So it's a potential divider, isn't it? Now, it does say that there might be an issue, or does suggest there might be an issue with the voltmeter because the voltmeter has a fairly low resistance for a voltmeter. Now, if you remember with voltmeters are designed, they should not interfere with the circuit at all. They should have as high a resistance as possible because if they draw current, they interfere with the circuit. So they should have a very high or near infinite resistance. Now, this fella has a resistance of 45 kiloohms. Now, the thermistor should be having a resistance of 9.7 kiloohms. So it wants you to comment on the suitability. And it wants a calculation. So the obvious calculation would be to calculate the effective resistance of these two in parallel. Okay. So remember the equation for resistors in parallel. We've got 1 over RT is 1 over 45 plus 1 over 9.7. Now I can leave those in kiloohms. I could convert them to ohms if I wanted to, but because we have three values of the same quantity, of the same unit, I can actually leave those as kiloohms here. So this gives us a total effective resistance of those two in parallel of 7.98 kiloohms. Now that's considerably less than the resistance of just the thermistor. So this is not ideal. Okay, that voltmeter is going to draw a significant current, not as much as the current through the thermistor, but it's still going to draw a current all the same. Okay, so you'd have to say that it's not suitable because the total effective resistance of those two in parallel is quite a bit less than what it should be. Okay. Right, explain why connecting the voltmeter across both the ammeter and the thermistor would improve this experiment. Right, if we go for a voltmeter across both of those, that's fine because this practical is then fine because the ammeter is just reading the current through the thermistor. Yeah, sure, some current will go this way through the voltmeter, but some will go through the ammeter. But as long as we have the thermistor, as long as we have an accurate value of I for the thermistor, we're fine. And don't forget, the voltmeter is still measuring the voltage across just the thermistor. Because the ammeter has zero resistance, putting the voltmeter here is still measuring the voltage across just the thermistor. So now we have the exact current through the thermistor and the exact voltage across the thermistor. So we can carry on with our practical. Okay, now finally, it's a negative temperature coefficient. It's an NTC thermistor. With reference to charge carriers in the thermistor, explain what happens to the potential difference across this thermistor as it warms up. So, okay, it's NTC, so as it warms up, resistance is going to go down. Now, if you remember, when we studied semiconductors, okay, it's all about band theory, isn't it? Okay. Now, with thermistors are a semiconductor device. So they have a piece of semiconductor in them, a little slice of germanium or silicon. Okay. Now, as it warms up, resistance goes down. Now, the reason for that is it's all about, like it suggests in the question, it's all about charge carriers. Okay. Now, as you can see here, we have the valence bands in red and we have the conduction bands in blue. right? And if you remember, for metals, there's always an overlap. That's why metals are very good conductors of electricity. For insulators, remember the gap between valence band and conduction band is always large, is too large for electrons to jump into the conduction band. That's why they don't conduct electricity. But with semiconductors, that jump is 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 doable for a lot of electrons. Now, as the temperature increases, more electrons are released into the conduction band. If more electrons are released into the conduction band, we have more. The charge carrier density here will increase. That will be seen as a decrease in resistance. And if you remember, from because this is a potential divider, if the resistance of the thermistor goes down, the potential difference across it will go down because this is a potential divider. Okay, so if the resistance of this goes down, this will get a smaller share of the potential difference because it's a potential divider. Right, there you go. That was fairly straightforward, I thought. Okay.